28 of our series on numerical methods in civil engineering, we will continue with our discussion of differential operators, which we introduced last time. So, last time we looked at the forward difference operator and found a relationship between the forward difference operator and the derivative, right? And we found that the kth order forward difference operator is related to the kth derivative of a function through this sort of a relationship, right? And thus h to the power minus k delta k f x is an approximation to f k x, right? It is an approximation. Why? Because this is evaluated at xi, right, and that is evaluated at x, and the error of the approximation reaches 0 as k tends to 0, because xi must belong to the interval x to x plus kh as k tends to 0, and the error is approximately proportional to h, right. It is linear in h, right. We also saw at the end of last lecture that h to the power minus k delta k f x is a much better approximation to the exact derivative evaluated at x plus k h by 2 than it is to the derivative, to the actual derivative at x, and because the error in that case is quadratic in h, right. As you reduce h, the error goes as h square, right. And we also talked about other difference operators being the central difference operator, the backward difference operator, and the averaging operator, the average difference operator. And we define the central difference operator by delta operating on f of x is equal to this. The average difference operator mu operating on f of x is defined like this. The backward difference operator is defined like that, and we can also establish relationships between each of these operators, right. For instance, it is clear that delta f x minus h is equal to the forward difference operator operating on f x minus h is equal to the backward difference operator operating on f x, and similarly we can get similar relationships, right. Similar relationships can be obtained not only for the first order difference operators, but also for higher order difference operators. Some common relationships between higher order difference operators, well, del square f a, right, if you apply the central difference operator 2 times on the function evaluated at a, that is actually equal to del square f a minus h, right. It is equivalent to applying the forward difference operator 2 times on f at a minus h, and it can be shown that this is equal to f a plus h minus twice f a minus h. Similarly, if I have a function evaluated at a and I apply successively on that function the central difference operator, first I apply the central difference operator, then I apply the average difference operator, then I get something like this, right. Now, similar to the relationship between the kth order forward difference operator and the kth order derivative, which we just saw, right, which we just saw in the previous slide, which was this one, right. Similar to that relationship, we can get relationships between the central difference operator and the derivative, right, the kth order central difference operator and the kth order derivative, right. And the relationship actually is something like this, right. It says that the kth order derivative of a function is related to the kth order central difference operator like this, plus these terms, right, and you can see these are terms involving h square, h4 and so on and so forth, and they also involve the derivative of the function, higher order derivatives of the function evaluated at a. So, if I am interested in f prime of a, right, and I want to find how my central difference approximation to f prime of a is related to f prime of a, I use this relationship, right. This tells me that f prime of a is approximately equal to the central difference operator acting on f a, right, scaled by the appropriate step size, plus the error terms. And how are the errors, what are the error terms? Well, the error terms go as h square, h4 and so on and so forth. The leading order of the error term is given by h square, right, and it also involves the partial higher order derivatives of f, right. So, f k plus 2, right. So, the right hand side includes only even derivatives of f. Also the constants C L are independent of f. So, these constants, right, they do not depend on the function, but they do depend on the order of the derivative that we are interested in, right. These constants depend on k, right, they depend on the order of the derivative. So, from this previous expression it is also clear that for second or third order polynomials, the derivative approximation that I get using the central difference operator is going to be exactly equal to the actual derivative. Why? Because these terms f k plus 2, f k plus 4 are going to be 0, right. These are going to be 0, right. These are going to be 0. So, it is clear that for second degree or third degree polynomials, right, f double prime of a is equal to del square f a by h square, right, and this is equal to this we have already seen del square f a, which we have seen to be this, right, we have seen that to be that. So, it is clear that for second degree or third degree polynomials, the second derivative is exactly predicted by the central difference operator acting 2 times on the function, right. Thus, in this case theoretically the second central difference operator is exactly equal to the second derivative of the function irrespective of step size, right, which is very important, right. So, whatever be my step size, right, whatever be my step size, if I find the derivative using this little formula here, that is going to be exact, right. That is going to be an exact that is going to give me the exact second derivative of the function. That is going to give me the exact second derivative of the function, right. And why do I say theoretically? Well, it is always theoretical whenever you do numerical approximations like this, is always you say theoretical because of the possibility of round off, right, because of the possibility of round off. Because this f a plus h is going to be calculated using finite precision arithmetic, we are going to miss some terms. So, that is not going to be exactly equal to the analytical derivative f double prime of a, but within those round off, within the limits of those round off errors, right, this is the exact derivative for second degree or third degree polynomials. In practical applications, that is what I said again, right, in practical applications of results such as that, right, it is clear that computations such as above will involve round off errors and they will have significant effect on the accuracy of the higher differences and thus their ability to represent the exact derivatives, right, exact derivatives. Is that clear? Okay. Why do I say why do the round off errors become more significant for higher order higher differences than for lower differences? Well, you can see that once you have h square, once we are interested in the second derivative, we have h square in the bottom, right. Typically h square is going to be smaller than h, right. If I have third derivative, that will involve h cube in the denominator, right. So, the round off, so h cube is going to be smaller than h square. So, the round off, whatever the round off error is going to be more important for h cube than it is for h square, because h cube is much smaller than h square, right. Is that clear? It is apparent that using the difference operators to estimate the derivatives of a function requires knowledge of the function values at various grid points, right. So, I have to have my grid, right, like right now we are looking at 1D, later on we are going to generalize this into higher dimensions but even in 1D you can see that in order to evaluate these derivatives I must know the function values at those grid points, right. Question is, what if I do not know some of those function values, right, that is what we are going to look at next, right. So, we denote by interval x0, x1 through xn the smallest interval containing the points x0, x1 through xn, and by fk, f prime k, f double prime k the function value and the first and second derivative at grid point xk. So, this is some nomenclature, right. Suppose our knowledge of the function and its derivatives is incomplete. That is, we know the values of the function and possibly some of its derivatives at some points on the grid, but we do not know the value of the function say at some other point in the grid, say at point xi. And it turns out that for a certain difference formula that I have got to use to approximate my derivative, I need the function value at xi. So, what am I going to do, right? So, next we are going to discuss at a sort of systematic procedure to get those function values to at the unknown points, at the unknown grid points. So, what we would like to do is we know certain values, we would like to use the function and derivative values at the grid points where they are known to set up an approximation formula which would yield the function value at xi, where the function value is unknown, right. Now, the criterion is that this value should exactly match the function value at xi obtained by fitting a polynomial of the highest possible order through the known grid points x0, x1 through xm, right. So, I know the function values at x0, x1 through xn, right. So, the best approximation I can get is if I can fit a polynomial through those points, right. So, what I am saying is that I want to come up with an approximation formula for finding the function value at xi, but the criteria is that my approximation formula must give the same value, at least the same value as I would get if I fit a polynomial through those n plus 1 points, right. So, using n plus 1 points, I can fit the best highest order polynomial I can fit through those points, it must be of order n, right. So, that is must be of order n, right. So, since the polynomial of highest order that can be completely defined using n grid point values, right, and there is a little error there, right. So, that is actually, but let us suppose that this is up to xn minus 1, right. So, x0 x1 through xn minus 1 is of order n minus 1. This means that the approximation formula must yield the same value of the function at xi as predicted by this n minus 1th order polynomial, right. So, if I fit the highest order polynomial, the value that it would predict at xi must be given by my approximation formula. Now, any such approximation formula will have errors associated with it. Why will it have errors? Well, suppose I have these function values at those points x0, x1 through xn minus 1, right. Suppose the function values are actually generated by a function which is of a higher order than my polynomial, that a highest order of polynomial, right, which was n, right, which was n, right. So, suppose, or rather n minus 1, right. So, if it is higher than that, if I actually generated the function values using a higher order polynomial, then the value that I am getting with my approximation formula is going to be inexact, because my approximation formula can only give the highest, it can only be as accurate as the highest order polynomial that can be fit through those points. Suppose I generated values at those points using a higher order polynomial, then my approximation formula is not going to give me the right value at xi, right, at xi, because at xi the actual value is going to be predicted by that much higher order of polynomial. Is that clear? Right. So, these errors will include truncation errors. For example, in our example just considered, if the function which actually gave rise to the known values at the grid points were of a higher order than n minus 1, for example, of order n or higher, then the value we are going to predict at xi will be inexact, because our value will only be as good as n minus 1, right. It will not predict, it cannot be exact if my value at xi was actually predicted using a polynomial of a higher order, right. The magnitude of the error in this case will be given by the truncation error, right, with the leading order term in the error given by a term of order n, right, because that is the term which I am throwing away, right, that is the term which my approximation formula cannot capture. All lower order terms my approximation formula can capture. Terms higher than that n minus 1, which is the first term which I cannot capture, is of order n, right. So, my error is of order n. So, other sources of errors include round off errors due to uncertainty in the input data, right. For instance, I know only my function values up to the round off errors. At the known points, at the known grid points, I do not know the function values exactly, I only know them up to the round off error. So, those are the errors that are inevitable, right, that are inevitable. So, one way to reduce the truncation error is to reduce the spacing between the grid points. So, if you make the grid points closer and closer while their number is held constant, the truncation error is going to reduce with grid size, right. As you make your grid finer and finer, right, the truncation error is going to reduce with grid size. In our example, if the grid size reduces from h to h by 2, the error will reduce by a factor of 1 by 2n, right, because the error goes as n, right. So, if I reduce the grid size from h by h2, my error will be reduced by a factor of 1 by 2n. So, what I am saying is that I keep my number of known points the same, right, but suppose that at the locations at which those function values are known become closer and closer. So, my grid size becomes smaller and smaller, right. In that case, my error is going to go down, right, and my error in this case is going to go down by 1 by 2 to the power n. However, the work of computing function values often increases sharply as the grid size becomes smaller, right. As my grid becomes smaller and smaller, right, the work of the computation becomes more expensive, right, because I have to deal with smaller numbers, right. In addition, round off errors become more and more significant as grid size increases, right. As the grid size increases, the round off errors become larger and larger. For example, if the machine precision is say 10 to the power minus 3, then it makes no sense to make the grid size h below 10 to the power minus 3, because any reduction in truncation error due to the smaller grid size is because the round off error is going to be nearly as large as my grid size, right. So, it makes no sense to make the grid size smaller than the round off error, right. Then whatever increase I am getting in reduction in truncation error because of the smaller grid size is going to be offset by the round off error, right, because it is going to be offset by the. So, if the machine precision is of the order of 10 to the power minus 3, it makes no sense to reduce the grid size below 10 to the power minus 3. So, what do we do? What do we do? Suppose I know I can only, so I am saying that even if you make your grid size smaller and smaller, it is not going to be of much use, because after a certain point your round off error is going to annihilate whatever whatever reduction in truncation error you achieve by reducing the grid size, right. So, what am I going to do? Well, it turns out that there is a method called the Richardson extrapolation technique, which comes to our aid. Why does it come to our aid? Well, basically we want to find the function, we want to get an estimate when the grid size actually becomes 0, right. We want to get an estimate of the function value at xi at an unknown point. I want to find the function value at xi when the grid size becomes 0. I know that when the grid size actually becomes 0, then my truncation error is going to go to 0 as well, right. So, I want to find the value of the function at xi when the grid size goes to 0. But I know that in actual practice, if I actually go on trying to reduce the grid size to 0, I am not going to get anywhere, because after a certain point my round off error is going to become so large that it is not going to help. So, then I use this extrapolation technique. So, what do we do? Well, suppose the current grid size is h, and suppose we can evaluate the function values at this grid size, which we denote as f of h, right. Suppose for a grid size h, we can find out the function value at xi, which I am going to call f of h, right. So, we would like to know the limiting value f of 0. So, I would like to know the function value at xi for a grid size 0, right. So, for f of 0 as the grid size approaches 0 without having to make the grid size extremely small, right, without having to go through that pain and ultimately futile exercise, that painful and ultimately futile exercise of making the grid size extremely small. In order to know, so we can use Richardson extrapolation provided I know how the function behaves as h becomes smaller and smaller, right. Suppose I know that as h goes to 0, f of h is given by this relationship, right. F of h is equal to a0 plus a1 h to the power p plus order h to the power r greater than p, right. Suppose I know that the behavior of the function as h becomes smaller and smaller is reasonably predicted by this equation, right, by this equation with the h to the power p and the order of the error is of the order of h to the power r, right. So, basically I want to find out a0, right, because when h goes to 0, f of 0 is equal to a0, right. So, I want to find out a0. I do not know what a0 is. I have some idea of p and r, but I do not have any idea of what is a0 and a1, right. I know that as my h becomes smaller and smaller, the function value goes as h to the power p, right. The function value changes as h to the power p, right. I have some idea of that factor p, right, but I do not know a0 and a1, right. So, according to Richardson extrapolation, we can calculate a0 and a1 if we know f for two step lengths h and qh, where q is greater than 1. How do we do that? Well, we evaluate f of h at step size h, right, and we evaluate f at step size qh, right. Using these f of h and f of qh, I can solve this set of equations to find out what is my a1, right. I can solve these two set of equations to find out my a1. Once I find out my a1, I can find out my a0, right. Substituting the value of a1 in this equation, I can find out what is a0, and once I know a0, I know what is f0, right. So, if it turns out that a0 comes out as f of h plus f of h minus f of qh by q to the power p minus 1 with this error term, right, error term. So, if I can find out the function value at h for step size h, if I can find out the function value for step size q of h, and then I know that as the step size becomes smaller and smaller, I know how the function behaves. So, I know p, right, then I can find out what is the function value for step size 0, right. So, this allows us to actually compute the function value at 0 step size up to this error term, it allows me to compute that function value at 0 step size, even if without reducing the step size, making the step size infinitesimally small, right. So if we know a more complete, this we know only up to the first term, right, the first term if I know how f behaves near the 0 step size only up to the first term in that series, but if I do more terms in that series, right, then I can do this repeatedly, right. Let us see how we can do that. If we know a more complete expansion of f h in terms of powers of h and unknown coefficients, then one can repeatedly use the Richardson extrapolation technique to get better and better estimates of f0, right. So, the repeated application of Richardson extrapolation becomes simple when the step lengths form a geometric series h0 by some factor, h0 by square of that factor, and so on and so forth, right. So, here we have in this example we have just used Richardson extrapolation once, right, because we only know the leading order term in the series. if I know more terms in the series, I can use Richardson extrapolation repeatedly, and once I use it repeatedly, this error which was there of order of HR, it is going to become smaller and smaller. So, I can know the value of f0 more exactly if I use this repeated Richardson extrapolation, but in order to use that repeated Richardson extrapolation, I must know how FH behaves up to, I know the series expansion for higher orders of, in terms of higher orders of H also, right. Suppose we know that as H goes to 0, FH goes like this. FH is equal to A0 plus A1 H to the power P1, A2 H to the power P2, AK H to the power Pk, and so on and so forth, with all these coefficients being increasing, right, increasing. So, P1, P2 is greater than P1, Pk is greater than P2, P3 is greater than P2, and so on and so forth, right. Then if we set F1 H is equal to F of H and iterate to obtain Fk plus 1 H is equal to, then we use this little iteration formula, right, and we iterate repeatedly, and we start with saying that F1 is equal to F of H, right, and then we use that to calculate F2, right. F2 of H is equal to F1 of H plus F1 of H minus F1 of QH divided by Q to the power P1, Q to the power P1 minus 1, right. So, that will give me F2. Then again I use that to calculate F3, F4, and so on and so forth. Then it can be shown that Fn, if I do this n times, right, Fn of H, the series for Fn of H is actually given by A0 plus An to the power n times H to the power Pn. Notice this coefficient is most important, right, H to the power Pn, then plus An plus 1 some constant H to the power Pn plus 1, and so on and so forth, right. Now, let us go back and look at this. F of H was given by this, right, F of H was given by this, and you can see the leading order term is of power P1, right. But after I have iterated n times Fn of H, after n times Fn of H, the leading order term is of power Pn. Pn is much higher than P1, right, as we saw before, right. This shows that as the number of iterations increases, Fn of H comprises, other than A0, terms that involve higher and higher powers of H, right. Thus, as I do this iteration repeatedly, Fn of H becomes a better and better estimate to A0 is equal to F of 0, right, because these error terms become smaller and smaller and smaller, right. How can we prove this? Well, to prove this, we recall that star, meaning this we said holds for F1, right. If it holds for F1, suppose it holds for n is equal to k, right, then we can calculate Fk plus 1 H from Fkh, right. We can use this formula. Let us suppose that it holds for Fk, then we can calculate Fk plus 1 H using that formula, right, and it will involve the same powers of H as the expansion of Fkh. Why? Because Fk plus 1 H is directly computed from Fkh, right. So, we can expect that Fk plus 1 H will involve the same powers of H as Fk, right. So, now let us see let us know that in the expansion of Fk plus 1 H, the coefficient of H to the power Pk, let us find out what is the coefficient of H to the power Pk, right. I know that Fk, the leading order term in Fk is given by H to the power Pk, right. Let us find out what is the coefficient in Fk plus 1 of H to the power Pk. Well, it turns out that it is like this. So, Fk plus H, so that is A to the power Pk, right. So, A to the power Ak to the power k, right. H to the power Pk will have Ak in front, right. So, that will be Ak, the coefficient, right, minus Fk QH, right. ak, if I evaluate fk with qh, it will be h to the power pk times q to the power pk. So, now the coefficient will be ak q to the power pk, right. The coefficient of h to the power pk, if I use a step size qh, is going to be ak q to the power pk. So, it will be ak minus ak q to the power pk divided by q to the power pk minus 1, and of course, this term which is akk, which is coming from that term, right. The coefficient of h to the power pk will be ak, right. So, if you add these two, add all these terms together, you will find that this is becoming 0, right. This is becoming 0. So, what does this tell me? This tells me that although I generated fk plus 1 h using fk, I did not use anything else. I just got fk plus 1 h using fk of h, right. Although I generated fk plus 1 using fk, it turns out that when I go through this operation, I have got rid of the first term in the X series expansion for fk, right. The next terms are there, hpk plus 1 is there, but the coefficient of hpk has become 0. So, in the expansion for fk plus 1, the leading order term is hpk plus 1. It is no longer h to the power pk, right. So, that means that every time I do this, I annihilate more and more terms, right. I annihilate more and more terms. This means that fk plus 1 h will not contain any terms of order h to the power pk and will contain terms of h to the power pk plus 1 or higher. This implies that the result holds for n equal to k plus 1, and this completes the proof by induction. So, if we know that it holds for f1, we assume that it holds for fk. If it holds for fk, it has to hold for fk plus 1. So, since it holds for 1, it holds for 2, it holds for 3, it holds for any n, right. So, we see that as we do this repeatedly, what this proof tells us is that if we apply the if I apply the Richardson extrapolation repeatedly, then I am going to get higher and higher, or higher I am going to get f0 with greater and greater accuracy, right. The error is going to reduce. Okay. So, why did we go into that? Because we said that we have to evaluate the function values at the grid points, right. And suppose I do not know, if I have to evaluate my we have to evaluate a certain difference operator and I do not know the function value at a required grid point, then I can use this approximation method to find out the function value at the grid point, right. And but the approximation method is only going to be as good as the highest order polynomial that I can fit, right. So, there are inevitably going to be errors, and those truncation errors are going to be of order higher than the highest order polynomial that I can fit, but I have this. And so, there are two ways of reducing those truncation errors. One is to reduce the step size, but then I found that if I reduce the step size below a certain value, that is useless, because my round off errors are going to dominate and they are not going to give me any further advantage. So, then I talked about the Richardson extrapolation technique, which allows me to find out a more exact value of the function at xi, even close to what I would get if I used a step size of 0, right. If I use a step size of 0 without encountering those round off errors, right, without encountering the round off errors, that is without actually evaluating the function value for 0 step size, right. So, that was the idea, right. That is a brief recapitulation of what we discussed. Okay. So, now let us look at another way, and there is some very important very important way of obtaining difference formulas, right. So, up till now the difference formulas we have got, we just defined them, right, we just defined them, right. But there it turns out that by using something called operator calculus, it is possible to come up with these approximation formulas for those derivatives, right. So, the difference operators we have considered thus far can be operated on using the rules of algebra and calculus to find more approximation formulas, right. However, this requires making assumptions on the continuity and derivability of the space of functions on which these operators are defined. For the sake of simplicity, we assume that our functions are infinitely differentiable, right. For the sake of simplicity, we assume that. And we also assume that our operators are linear, right. If the operators are linear, what does it mean? Well, it means that if P is a generic difference operator, anything like delta mu or whatever, right. P is any generic difference operator, and f and g are functions that belong to the domain of the operator, that is, they possess appropriate differentiability properties, right. Then P operating on alpha f plus beta g is equal to alpha P operating on f plus beta P operating on g, where alpha and beta are scalars, right. We also assume that the operators are commutative, that is, if I operate on f with first q and then p, that is the same thing as if I operate on f with first p and then I operate on the result with q, right. And then I make a further statement, which is that when can I say that two operators are equal? Well, I can say the two operators are equal if they give me the same result for all functions f. So, if I operate with P on a space of functions, the space of functions include all possible functions with the appropriate differentiability properties, and I find that the result is equal to what I would get if I operate with the operator q on that same space of functions, then I can say that my operators p and q are the same, right. So, I know the equality stems from the result, right. So, p is equal to q if the result that I get if I operate with p on all the functions belonging to the function space of interest is the same as I would get if I operate with q on that same function space, right. Okay. So, let us look at some examples of the use of operator calculus. In order to do that, let us look at our Taylor series of f x plus h. So, f x plus h is equal to that, you know, from Taylor series, right. Now, this I can rewrite this in terms of the shift and the differential operator. How? Well, what do you have on the left hand side? You have f x plus h. So, I can write that as the shift operator operating on f, right, and the right hand side I have the differential operator, right. So, I can write this as e of f of x plus 1 plus h times the differential operator plus h d operating 2 times on f of x, right, which I denote as h d square, right, h d square, right. Then I have h d operating 3 times on f of x, which I denote as h d cube. So, you see h cube by 3 d cube f of x, right. So, that I am denoting as h d operating 3 times on f of x. So, h d to the power cube divided by factorial 3 operating on f of x, right. Thus, it is clear. Now, look at this series, right. What is that series? That is an exponential series, right, exponent of to the raised to the power h d, right. So, that thus it is clear that E is equal to h d, right. So, operator calculus allows us to get this relationship between the shift operator and the differential operator, right. The shift operator can be expressed as the exponential of the differential operator scaled by the step size. Recall that we showed earlier that the shift operator is actually 1 plus the forward difference operator. We showed that, right. So, this means that E raised to the power h d must also be equal to 1 plus delta, right. We take log of both sides, right. Log of e to the power h d is equal to h d. Log of 1 plus delta, I can expand it in series, right. log of 1 plus delta. If I expand in series, I get delta minus delta square by 2 plus delta cube by 3 and so on and so forth, right. Therefore, HD operating on f of x, now I am looking at this operating on f of x is equal to h f prime of x by definition, right, because D is nothing but the differential operator, is equal to h f prime of x is equal to this operating on f of x, right. So, what does this tell me? This tells me, my operator calculus tells me that the exact derivative is actually equal to this series operating on f of x, this series which involves the forward difference operator operating on f of x, right. So, not only does it involve delta f of x, it involves del square f of x, it involves del cube f of x and so on and so forth. So, that is sort of frightening, right, because in order to estimate the first derivative, it tells me that you must take like infinite differences, right, infinite differences, which tells me what, why, when, how is that going to work, right. If I have to take infinite differences in order to estimate my first derivative, this whole thing is unworkable. But we must remember that these differences go like this, h to the power k f of k, right. This difference is del k f of x goes as h to the power k times f derivative of f, right. So, if so it becomes smaller and smaller, right. The contribution of these higher order differences are smaller and smaller, because they are proportional to h to the power k, right. So, for my step size, suppose if I have my step size 0.1, so and then the contribution of del n, del raised to the power n is going to be 0.1 raised to the power n, 0.1 raised to the power 10, right. So, that is going to be something like 10 to the power minus 11, right. So, eventually those higher order terms are not going to contribute much. So, I can throw out those I can ignore those contributions, right. So, the above example shows how operator calculus can allow us to establish relationships between various operators, in this case the D and the delta operator, right. So, for an example, let us consider the function E x is equal to e to the power alpha x. Why do we consider it? Because we assume that the function has to be infinitely differentiable. So, that e to the power alpha x is infinitely differentiable. So, from this we get h d e to the power alpha x is equal to this delta minus del square by factorial 2 plus del cube by factorial 3 and so on times e to the power alpha x. It can be shown that this holds for all polynomials. It holds for all polynomials. Recall our earlier result, right, del k f of x is equal to that, right. If f is a polynomial of degree m, we are going to have only n terms on the right hand side of star, right. So, that is one saving, right. So, if the function f, right, is a polynomial of order n, so the higher order differences are going to disappear, right, because the higher order differences are proportional to the derivative, right. Higher order polynomials after a certain order are n plus 1 derivatives, n plus 1 and higher polynomial of order n plus 1 and higher derivatives are going to be 0, right. So, those things are going to disappear. So, the difference is also going to get truncated, right. But even so, that is one saving, right. So, for a higher order polynomial, we know that after a certain order the differences are going to be by definition 0. But again, even the higher differences, even that does not mean that we have to calculate differences up to order n, right? No, absolutely not, because those differences are going to be proportional. Difference of order n is going to be proportional to h to the power n. So, its contribution for a reasonable choice of step size is going to be negligibly small, right. It is going to be probably less than round off, right. So, we can make sensible choices of how many terms we need to take, right. So, if f is a polynomial of degree n, we will have only n terms on the right hand side of star, because terms involving delta n plus 1 or higher will be equal to 0, since f n plus 1 and higher order derivatives are 0. Thus, star gives the formula for the exact numerical differentiation of an nth order polynomial involving the operator delta. It is exact, but we are never going to use it exactly, right, because those higher order differences are going to give me smaller and smaller contributions, right. We can similarly establish relationships between the derivative operator and the central difference operator. So, we got a relationship between the derivative operator and the forward difference operator. We can similarly establish relationships between the derivative operator and the central difference operator. How? Well, let us see. We know that del f of x is equal to f of x plus h by 2 minus f of x minus h by 2, right. This I can think of as a forward difference operation, right, forward difference operation. Remember, I know, or sorry, not the forward difference operation, my apologies, as the shift operation, right. I know there is a relationship between the shift operator and the exponential, right. I know there is a relationship between the shift and the differential operator using the exponential function, right. So, in this case, if I look at this again, f of x plus h by 2, I can think of that as a shift operator, and now the shift operator has step size h by 2, right. My shift operator with step size h by 2, and I know that my shift operator with step size h is related to the difference operator by e to the power h d. So, my shift operator with step size h by 2 is related to my differential operator by e to the power h by 2 d, right, e to the power h by 2 d. So, this I can write as f of x plus h by 2, I can write as e to the power h by 2 times d. F of x minus h by 2 I can write as e to the power minus h d by 2, right, and this operating on f of x, right, this operating on f of x. What is this? That is nothing but my sine hyperbolic d by 2, sine hyperbolic d by 2 divided by 2, right, sine hyperbolic d by 2 divided by 2. So, that times f of x. That is what do we get? So, operator calculus tells me that the operation of the differential of the central difference operator on f of x is equal to sine hyperbolic of the differential operator by 2 divided by 2 operating on f of x, right. So, hence del is equal to 2 sine hyperbolic h d by 2, since the two operators are equal if their action on a function gives me the same result, right. So, this central difference operator operating on f of x is equal to this operator operating on f of x. So, I can say that my central difference operator is equal to this operator, right, because we said before that equality of the operators means if the equality of the results on the same function, right. If I operate with two different operators on the same function and the results are the same, then I am going to say that my operators are going to be the same, right. And since I said that that must be true for any arbitrary function, my f of x is any arbitrary function which satisfies the appropriate differentiability requirements, right. So, we get this expression delta is equal to that, right. And then if I go back, I can, so then I take a step back and I say that if I can always expand x in terms of a series in sine hyperbolic x, right. I am not going to show that. You can see some books on good mathematics books on infinite series, right. You will see that you can always expand x in terms of a series in sine hyperbolic x. So, since we can do that, but we know that sine hyperbolic d by 2 is equal to half of my difference operator, right. So, if I expand hd by 2, I can expand hd by 2. If I treat x as hd by 2, right, I can get hd by 2 in terms of a series in sine hyperbolic hd by 2, right, sine hyperbolic hd by 2. But sine hyperbolic hd by 2 is equal to delta by 2, right. Sine hyperbolic hd by 2 is equal to delta by 2. So, I can get a series for hd by 2 in terms of delta, or rather delta by 2, right. So, that is exactly this series, right. So, hd by 2 is equal to delta by 2 minus half delta by 2 cube by 3 and so on and so forth. And finally, we get a series like this, hd is equal to delta minus delta cube and so on. So, this gives me a very similar relation, similar series to the series I got between the forward difference operator, between the forward difference operator and my differential operator, right. The series that I got between my forward difference operator and the difference operator, right. So, there I got hd in terms of delta minus delta square by 2 and so on and so forth. Here I am getting hd in terms of the central difference operator, central difference, that was in terms of the forward difference operator, this is in terms of the central difference operator. Gives an expression for the exact differential operator in terms of the central difference operator and its higher orders. So, here by using this operator calculus, we are getting these series expressions, right, series expressions for my exact differential in terms of my difference operators. But this should not scare you, right, this should not scare you, because you should realize that these higher order difference operators are going to have negligible contribution, right, their contribution is going to scale with the step size, right. So, it is not that if we have to find out the exact differential, I have to find out all these terms in the series, absolutely not, right. We only need to compute some terms in that series, only some terms in that series are going to contribute significantly meaning it will not be lost in round off, right. Only some terms in the series are going to give significant digits, right, which are not going to get lost in round off. But this gives some insight, right, it's not, maybe it's not that practical, nobody is actually going to use that series, right, but it gives some insight into how the behavior is. Similarly, by squaring this series twice, we can get an expression for the differential operator 2 times, right. If I square it, we get an expression for d square, which is my second derivative, my differential operator acting 2 times, right. So, I can get hd square. Similarly, analogously, I can get a series in terms of the central difference operator for my nth derivative as well, right, nth derivative as well. Now, there are some problems with direct applications, particularly for the central difference operator. There might be some problems. Why is that? Because the central difference operator requires us to know the function values at mid step, right. Suppose I only know the function values at h, 2h, 3h, 4h. If I have to use the central difference operator, I have to know the function values at h by 2, h by 3h by 2 and so on and so forth. So, using the central difference operator sometimes present difficulties. So, next class, before moving on to something and its other things, we will talk about how we can use a combination of the average difference and central difference operator to get around this problem. Okay. Thank you.